to demonstrate how the Bayes rule or the Bayes theorem works, I'm going to use this example of a test. So suppose we want to test if a person has a certain disease. And we know without any tests that we estimate, right, that about 1% of population has the disease. So we could say that the prior probability that the person is positive, meaning that they have the disease, which will be denoted as probability of P standing for positive, will be 1%, right? And this is necessary, otherwise we cannot apply the Bayes theorem. So we have to have some kind of best estimate for prior probability. And we also have a test that is 98% sensitive and 90% specific. So what that means is actually shown here. 98% sensitivity means that for people who are positive, who have the disease, 98% of them test positive with the test that we're talking about, that we're using. So that means, this is how you evaluate the tests. How would you evaluate a test? You try to find a group of people who definitely have the disease that you're trying to test for, and then you test them. And among them, you find out how many of them actually test positive. And so you get this conditional probability, right? This is we read this probability test is positive, given that we know a person is positive, they have the disease, right? So you have to have a group of people who are positive. And you see, this actually shows you how imperfect the test is. If the test was perfect, this would be 100%. If a person has the disease, they should test positive. But unfortunately, not all information events, or in this special example, not all tests are 100% accurate, right? And so that's sensitivity. And the other parameter is specificity, right? And specificity is when you take a group of people who definitely don't have the disease, we say they are negative, N stands for negative here, and you test them, and then what's the percentage of people who actually have the negative test result? So this is probability test is negative, given the person has no disease, and this is only 90%. It's even worse than the sensitivity, right? So again, if this test was perfect, both of those numbers should be 100%, and then the test would be a kind of perfect information. But this test is not a perfect information, and therefore we see that the quality of information that we will get afterwards will not be decisive, 100% decisive. So if we have this conditional probability, 98%, we can also calculate what's the probability that somebody tests negative given that they have the disease. And I hope you realize that, right? This is one group of people that we're testing here is people who definitely have the disease. If 98% of them test positive, it must be that the rest, which is 1 minus this, equals 1 minus this, that's 2% of people who have negative test result, given that even though they actually have the disease, which we know from other factors, right? So these we can call false negatives because, right, these actually are tests results that are negative, even though they should be positive, right? They are incorrectly identifying people. And then if specificity says probability of test negative given a person doesn't have the disease is 90%, then that means that of those people who don't have the disease, 10%, the remainder of those people must be testing as positive. So false positives in this case are 1 minus 90%, which should give us 10%. Now, the thing that to recognize here is that what we have is conditional probabilities that say probability of a test result given the actual status of the person, right? Even the actual positive or negative, right, information about the person. So we know that if a person has a disease, what's the probability they will test positive or negative? Or if the person doesn't have a disease, what's the probability that they will test positive or negative? But the interesting thing is the opposite conditional probability, right? Suppose you take a person and you don't know if they have a disease or not. If the person tests positive, right? So this is given that they test positive, you test them, you know TP, right, is true or false, that they tested positive or they tested negative, right? What is the probability that they have the disease? So in fact, what we want to know, right, is probability. Are they positive given that they tested positive, right? This is the kind of probability. And we can actually list the other probabilities. What's the probability that they actually are negative? We could put N here, right? Given they test positive. Or if they test negative also, we want to say, so for example, we can ask, what's the probability that they are actually negative given that they test negative, right? And I hope you see that these are conditional probabilities that have those two terms reversed compared to this, right? And don't think that it is just, you could just use one of those, right? For example, 98% as an answer for this. The reality is much more complex. So I created here a table that will help us, actually two tables, that will help us apply the Bayes rule or Bayes theorem. So the Bayes theorem tells us that if you want to obtain probability of an event given some information about this event, you can calculate it from probabilities, the prior probabilities of event. In this case, right, it's the probability the person is positive or negative, and conditional probabilities of how good the information predictive power is for people who have the disease or not. So these are the probabilities that are here, right? So from those, we can calculate the interesting probabilities using the Bayes theorem. Now, this is a bit of a complex formula if you want to do this calculation by hand. Easy to make mistakes, but very easy to formulate it in Excel. And in Excel, you can put it like this. You can create first a table for test positive. So this is for one outcome of information. That information could tell us the patient tested positive, right? We can put prior probabilities. There will be a bit of redundancy between those tables, right? Prior probability is this on the right, and we can actually calculate probability the person is negative is 1 minus, oops, 91%, which is 99%. So probability that the person doesn't have a disease is 99%. These are prior probabilities. Without the test, if you take a random person, you will know that 1% chance that they have the disease and 99% chance they don't have the disease. Now we need conditional probabilities, but be careful. These are conditional probabilities that the person tests positive given that X, and X is P or N, depending on which cell we're going, right? So this is test positive given they are positive, that's sensitivity, and test positive given they don't have the disease, that's this number here, right? That's false positives, right? So this is 10%. And the important thing is, notice these numbers do not add up to 100%, which is, they could, but just by chance, normally they don't add up to 100%. However, these two, right? Actually, I could put a sum, right? These two add up to 100%. I'm actually going to change it to general, just one, so that they don't cloud the important probabilities. This is just a check, right? Now, what do we need to do here? We need to calculate product of these two probabilities that we calculated before, right? And this is called joint probability. So this is what you see here in the numerator or as elements of the denominator, right? They are conditional probability information given event times the probability, prior probability of event. This is the first element, and this is the second element. So I can just say equals this times this conditional information, right? So this gives me a probability. I can copy it here. These two give me probability that the person has the disease and they tested positive. And this is the probability that they don't have the disease and they tested positive. And I hope you see there is a huge disproportion here, right? And if you add those probabilities, that will give you the result, the summation in the denominator. In this example, there's just two terms in this summation, right? So there will be a sum here. Those two terms give us the probability that the test will be positive. So, right, if you test a person, if you'd like to know, regardless of whether they have the disease or not, what's the probability the test will be positive? It's 10.88% in this case. And now you see, I can calculate conditional probability by taking one of those elements, dividing by the summation, which is here at the bottom, right? So the calculation will be this one selected joint probability divided by the summation. Let me actually do a 4 here, and then I can copy. And I have the conditional probabilities that I am interested in, right? This top one is this probability, right? Probability that, right, this is equal probability the person has the disease given that they test positive. And this will be probability that the person doesn't have the disease given that they tested positive. So I want you to see already, before we actually calculate the other table, that from this analysis, actually the test appears to be very weak, very poor, because right after we tested the patient and we found out the test result is positive, there's only 9% chance, around 9% chance that they actually do have the disease. There's 91% chance still that they don't have the disease, right? Why this is the case, I will discuss a little bit later. Now let me calculate the same table for when the test is negative. When the test is negative, again, we have prior probabilities. Without the test, oops, this should be equal to here. And without the test, they are negative 99% chance. Again, I will put a summation here just to make sure the prior probabilities are 1 in total. Actually, we can put the same summation here. There should be 1 here. There should be 1 here when we calculate. And now conditional probabilities, be careful. This is probability the test result is negative given positive or negative real state of the person. So I need test negative given they are positive is here. It's 2%. These are the false negatives. They are negative even though they actually have the disease. And this is the specificity 90%. And again, notice these two do not add up to 100%. They might, but it would be a rare situation. Normally they don't. And so joint probability as before, again, we're applying this same formula, but now the information is test negative. In the first table, information was test positive. So we need to have the products of conditional probabilities and the prior probabilities, this times this, right? Then the summation to have the denominator, right? Let's actually change the format here. Excel is trying to be smart and adding too many digits. And then we want the division, joint probability divided by probability of the test being negative. And again, copy it here. Oops, I need to this, divide by this, and I put 4. For some reason, Excel is putting a lot of digits here, and I will copy it down, right? And you see the summation here is 1, right? And so this probability here, 99.98, is the other interesting probability that we wanted. If they test negative, what is the probability that they actually are negative? In this case, the test is very conclusive, right? We're almost 100% certain they actually don't have the disease, right? And this would be probability that they do have the disease, P, given they test negative. So you see this is the base analysis, and I will show you some sensitivity analysis, right? I'll try to play with these parameters to see how they affect the result. But the most important conclusion from this is that even though we test a person and the person shows, the test result shows the person should have the disease, there's only 9% chance that they actually do have the disease.